we talked about the branching structure in Matlab by using the if, else, and construct. Right? This kind of a construct allows us to take different execution paths based upon the conditionals, right? Based upon a certain condition that's evaluated to either true or false, and we can, and then MATLAB is going to pick a particular execution path, right? That's called a branching structure. When we talk about flow control, there's another very important flow control structure that's called loops, right? Basically, you are asking MATLAB to actually repeat a certain set of statements or certain sort of execution block to by a number of times, right? Just to repeat doing the same kind of thing again and again. That's called loops, right? And it's basically some kind of an iteration process, right? You repeat doing the same kind of thing by a number of times through iterating, and the MATLAB actually provides a complete set of statements allow you to do that. And today we're going to look at in this video we're going to look at one particular type of loops, which is called the for loops, right? And if you have used other kind of languages, C++, Fortran, maybe not Fortran, but Fortran is called do loops, right? But if you Java, for example, Java has for loops, and then Python, right? So many different languages, many different modern languages actually have this kind of structure, this kind of construct allows you to iterate. So we're going to look at one example. We're going to look at one specific example, which is actually the famous Fibonacci sequence. It looks like that. So we'll try to compute the Fibonacci sequence, basically. How the Fibonacci sequence is created, right? So Fn, the nth number. So Fibonacci sequence is basically a sequence of numbers. The reason that it's called a sequence is that it's not just a one number, it's lots of numbers actually. It's an infinite sequence. And then you can sort of give an index for each of the number in this particular sequence. The nth number in this sequence equals to its previous number. So n subtract 1's number plus the n subtract 2's number, right? So every number is the summation of its two previous neighbors. That's for n larger than or equal to 2, right? So this formula is applicable when n is larger than or equal to 2. And when n equals to 0, then the Fibonacci, that's the first number actually. That's the first number in the Fibonacci sequence, and it has a value of 0. And then the second number, f1, actually equals to 1. Right? These two numbers are kind of fixed, 0 and 1. The first two numbers are 0 and 1. Right? And then for all the rest of the numbers in this Fibonacci sequence, they are just following this particular rule. Right? And if you want to get some kind of an explicit formula, you can actually compute Fn by using n. If you know n, you can compute Fn using this really complicated formula, right? And it's going to give you a very, very good approximation to Fn when n is very big, right? But in our implementation, we'll try to implement it in two different ways, right? First, we're gonna sort of use the for loop to actually compute the Fibonacci sequence iteratively, right? And then we're gonna compare the results computed using our iterative program with this kind of explicit formula, with the results computed using this explicit formula, right? So we're gonna take two different approaches to implement the Fibonacci sequence, right? One is by using a for loop, writing a loop, and then the other one is by sort of using this explicit formula. And if we want to write a for loop, let's look at if we want to solve the problem in an iterative way, let's look at some examples. Let's look at just the first few numbers in the Fibonacci sequence, right? We already know that the first two numbers are given by 0 and 1. That's kind of given to us. That's fixed, right? So f0 equal to 0, f1 equals to 1, right? And then f2 must equal to fn equals to 2, right? So 2 subtract 1, that's 1. So f2 must equal to f1 plus f2 subtract 2, that's 0, right? 2 subtract 2, that's 0, so that's f0. So f2 must equal to f0 plus f1, right? f0 plus f1. So f0 plus f1, 0 plus 1, that's 1, right? And then what's f3? f3 must equal to the summation of its two previous neighbors. So it's f1 plus f2, that's 1 plus 1, that's 2, right? And then what's going to be f4? What's going to be f4, right? f4 must equal to f2 plus f3, that's 3, right? And then what's f5? f5 must equal to f3 plus f4. That's 2 plus 3, that's 5. Right? And then if you go on like that, f15 is going to equal to 610. Right? That's sort of once we look at some examples, we get a better understanding about how to write the code, right? Because this very abstract mathematical equation now becomes more concrete to us, right? It has materialized in our head, this particular rule, right? Now all we have to do is to actually come up with the code for implementing this kind of a calculation, right? So in this particular exercise, we're gonna look at the loops, right? And then we're gonna sort of practice a little bit about the Matlab's graphic capability. We're gonna make some symbol plots. In our car example, we have already seen how to make plots by using button clicks, right? But this time we're gonna start from very simple, probably the simplest plotting command, which is basically called a plot, right? We're gonna look at the plot function, right? How we can actually use the plot function to actually display results obtained by solving the Fibonacci sequence using this iterative way by writing loops and the Fibonacci sequence created using this explicit formula, right? We're going to compare these two sequences, right, by plotting them and then visualize the differences between these two sequences, between the sequence constructed using the two different ways. Okay, so now let's get back to Matlab and take a look at the code. So so this time we're gonna write the function directly. We won't actually do a script first. We'll just write the function, right? So our first implementation is gonna be the for loops using the iterative approach. So let's just create a function, new function, and then the output is let's call it f, right? And then the name of the function, let's call it Fibonacci. Right? Fibonacci. I don't know if Matlab actually has an intrinsic function called Fibonacci. Well, it's got a Fibonacci intrinsic function. So it's probably not a good idea for us to actually reuse that function name to write our own function. So I'll prefix it with my Fibonacci, and then the input argument is just going to be a single number, right? Let's call it n. Right? Suppose we want the nth Fibonacci number, right? And then that's the n, right? So when n equals to let me write a simple comment. Compute the nth Fibonacci number and the index of the Fibonacci number the output is going to be the Fibonacci number, right? So let's save it as my Fibonacci, right? And then let's think about how we can actually write this function, right? So if we look at this particular statement about the Fibonacci sequence, when n equals to 0 and when n equals to 1, and when n equals to 1, we have fixed numbers 0 and 1, right? And then only when n is larger than or equal to 2, you are going to use this particular formula for computing the Fibonacci number. So in principle, if you see this kind of a condition, right? In principle, we are automatically sort of thinking about the else if this kind of construct, right? Because now you have to make a decision about which equation you want to use or which formula you want to use based upon the value of n, which is actually the input, right? So when you try to write a code, when you see this kind of a description about this particular problem, you need to actually think about how do we actually map this kind of a description into a conditional or branching structure or Matlab branching construct, right? So the key here is for n larger than or equal to 2, right? That's the key. That's sort of the condition, right? When n is larger than or equal to 2, this formula applies, right? And when n is smaller than 2, that's either 0 or 1, then you're going to use these two formulas, right? So how we're going to implement this kind of condition, right? We're going to use the if else if else, right? So if n is smaller than 0, so if user has given an incorrect input, given an n that's kind of a negative number, then we should report an error, right? Error. Input must be a non-negative integer, right? We just stop the execution altogether. We just report an error message, right? Else if n, suppose n equals to 0. When n equals to 0, so here we are doing a comparison, right? Here we are doing a comparison. It's not an assignment, it's a comparison. So when n equals to 0, the formula actually tells us that it has a fixed value of 0, right? f0 equals to 0. So in this case, capital F, the output should be equal to 0, right? And then else if, so when Matlab actually comes to this particular else if, this else actually implies what? This else actually implies that n is already larger than or equal to 0, right? If n is smaller than 0, it's not going to even come to this particular line. It's not going to even look at this particular condition, right? If n is smaller than 0, it's just going to execute this particular statement and then exit the entire f construct, right? So when Matlab actually comes to this particular else if, this particular statement, it means n is already larger than or equal to 0. So in this case, all we have to do is to compare with 0, and then compare with 1, and then every other value that's kind of accounted for by that formula, by that kind of formula, right? So let me finish writing the else ifs, right? So when n equals to 1, so f is going to equal to 1, right? And then else, right? The major part of the code actually is in the else block. It's actually in the else block, right? So the situation for n smaller than 0 is accounted for here, and the situation for n that's equal to 0 is accounted for here by this one line, and the situation for n equals to 1 is accounted for by this line. And here, the only situation that's left is when n is larger than 1, right? Or larger than or equal to 2, basically, right? It must be an integer. So now let's think about how we can write this write this part of the code. Write this part of the code. So basically, if we look at this formula, Fn, the nth Fibonacci number, only depends upon its previous two neighbors, right? It does not depend upon the previous third neighbor, right? So for example, f3 only depends upon f1 and f2. It does not depend upon f0, right? It has no dependence on f0. So when you want to compute f3, you don't really need to know what's actually the value for f0, right? All you need to know is the value for f1 and f2. And when you want to compute f4, the value that you're going to need in order to compute f4 is just f2 and f3. You don't really have to actually have a memory of f0 or f1, right? So what does it mean, right? What does it mean? It means that all I need is basically three containers or three variables in order to actually loop through the entire sequence. Let's denote those three variables or three containers as A, B, and C here, right? So in the first iteration, we're going to put 0 into A and put 1 into B, right? And then C can be computed. The value inside of the C container can be computed from the value inside of A and B, right? So because C is just going to equal to A plus B, right? And then in the next iteration, what we have to do is to actually, once we have C, right, this C is going to become the B in the next iteration, right? And the B is going to become the A in the next iteration, right? And then in the next iteration, C again equals to A plus B, right? So it's actually quite important for us to actually understand what's actually the logic here, right? What's actually the logic here? So the equation that we're going to use, the actual equation that's we're going to use is just the C equals to A plus B. Basically, we're just adding A and B together and then assigning the value into C, right? But what's actually goes into A and B depends upon the iteration. So for the first iteration, A and B is assigned with 0 and 1, right? It's F0 and F1, right? For the first iteration, right? And then for the second iteration, A and B is supposed to become F1 and F2, right? It's supposed to become F1 and F2, right? So we're supposed to assign F1 into A and F2 into B, right? But if you think about it, what exactly is F1 and F2, right? Because F1 and F2 in the previous iteration is exactly inside of B and C, right? So now all you have to do is to actually convert the B and C in the previous iteration into the A and B in the current iteration, right? That's all you have to do. And then C again equals to A plus B. You just add A and B together and assign that value back into C. This line doesn't have to change, right? All you have to do is to change the content inside of the container A and B, right? And then for the next iteration, all you have to do is to actually convert the B and C in the previous iteration to A and B again. So that's gonna be the logic that we're gonna use to implement this particular for loop, right? So let's go back to the Matlab code and see how we are gonna do that in terms of the syntax. The syntax for doing a for loop is actually relatively straightforward, right? So for, that's a Matlab keyword. As soon as we type the for, that's gonna be a keyword, right? So you're gonna see it in blue. And then we're gonna sort of iterate from. So we're gonna need something that's called an iterator, which is basically a counter, right? So II is gonna account for the iteration number, right? II is gonna go from 2 to n. So this is the so-called for statement, right? That's the beginning part of a for loop. And then you also have every for statement must be paired with an and statement, right, to end the loop. And then the loop body is written in between. Right. So II is basically just like a tracker or counter to count how many times you have iterated, right? So here we are gonna use II to sort of to sort of keep track of the number of iterations from 2 to n, and n is the sort of the input, right? The user wants to know what's actually the nth Fibonacci number, right? So this colon is the so-called range operator. Range operator means what? Range operator means that, so 2 colon n is gonna give you a sequence, right? So if you sort of let's do some experiment in the command window. So suppose I type 2 colon 10. If I type this thing in Matlab in the command window, what you're gonna see is that a sequence of numbers that goes from 2 to 3 to 4 to 5 up to 10, right? So it's gonna 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So this colon is the so-called range operator, and later on we're gonna look at how to use this range operator in different ways. For example, if you only want the even numbers from 2 to 10, how to actually create those even numbers, right? Here you have odd numbers included, right? Suppose you just want the even numbers, you don't want the odd numbers, you want to get rid of all the odd numbers. How can you actually do that, right? So the range operator actually allows you to do this thing, which means you start with a value of 2, you end with a value of 10, and then you have a stride of 2. A stride of 2 means what? A stride of 2 means that you have to skip one number, right? So 2, if the stride is just a 1 by default, by 1, for example, in this kind of situation, then in this particular line, right, then the stride is automatically 1. The default value is 1. If the stride is 1, then you do not skip any number. It's 2, 3, 4, right? But if the stride is 2, then you have to skip one number. So 2, and then what's the following is that you have to skip one number, 3, and then you go to 4, right? So this way you get all the even numbers, 2, 4, 6, 8, 10, right? So here we are not having a we're sort of using the stride that's default to 1, right? So we are not really specifying a stride that's different from 1, right? And then what's gonna be our body, right? The body of the loop. But before we enter the loop, let's initialize A and B and C. So A is gonna equal to 0. That's F0, right? And then B is gonna equal to 1. That's F1, right? So now A has the value of F0 and B has the value of F1, right? But in principle, C, we can just write C equal to A plus B here, right? But because this particular line will need to be iterated many times, right? So this line has to go into the loop, right? So let's just control X and then paste it inside of the loop. Right, let's paste it inside of the loop. So what's going to be the sequence of execution here, right? So first, 0 is assigned to A, that's F0. F0 assigned to A, and then F1 is assigned to B, right? And then we enter the loop body. So the first thing it's going to do is that II is going to take a value of 2, right? So for the first iteration, II is going to take a value of 2. And then for the second iteration, II is going to take a value of 3, that kind of thing, right? Up to n. II eventually, if n equals to 10, then II is going to end with 10, that kind of thing. If n equals to 15, II is going to end with 15, right? So II is just a counter kind of thing, right? And then A is going to be added with B, so 0 is going to add with 1. That gives you 1. So C actually equals to 1. After this statement, C actually equals to 1 now, right? C actually equals to 1. So for the first iteration, C is going to have a value of 1, right? But as soon as we got the value of C, as soon as we got the value of C, right, we need to actually turn B. We need to actually put the value in B into A and the value in C into B, and then compute the next C, right? So how are we going to do that, right? We need to actually put the value of B into A, basically, right? We need to put the value of B into A again, and then put the computed C, the value in the computed C, into B, into the container B. And the order is kind of important, but let's write the code first. Right? So how do we actually put the value of B into A, right? How do we actually put the value in B into A? It's actually quite simple. All you have to do is to do assignment. Right? You just assign the value in B into A. Right? And then all we have to do is to actually put the value in B into C. So put the value in C into B. And it's again an assignment. Right? We need to put the value of B into A, and then the value of C into B. Right? Now we have updated the value of A and B now. We have updated the value of A and B with the values that's in the previous iteration of B and C. Right? And then the loop body has finished. Right? Because after the first iteration has finished, we have computed C, and then we have updated the value of A and B, and then the loop is going to go back to the beginning, and then II is going to take the next value, which is 3, and then redo this C equals to A plus B. Right? And then now A has a different value now, and B has a different value now. Right? A is not 0 anymore. For the first iteration, A was 0, but now A is not 0 anymore. Right? A is what? A is actually what? Right? A actually has a value of 1. Right? Because A has a value of the B value of the previous iteration. And in the previous iteration, B actually has a value of 1. Right? And then B should have a value of the value of C in the previous iteration, right? And the value of C in the previous iteration has a value of 1. Right? So now B has a value of 1 now. Right? So both A and B are going to have different values now for the second iteration. Right? And those new values are going to be used to do the addition and then assigned back to C. And then we update B, A and B again. Right? And then after we have finished the entire iteration, so II has reached N. II started with 2, right? And then it's going to go through 3, 4, 5, and then eventually it's going to come to N. And when II reaches the value of N, the loop has completed. So Matlab is going to come to the end statement and stop executing this loop anymore. It's going to exit this particular loop. And at this point, we have actually finished computing Fn. So all we have to do is to assign C to F. And this way we have finished computing our function, right? I was saying that the ordering of these two assignments is actually very, very important. If you actually put C into B first before you actually put B into A, then you're going to have a logic error. And this kind of error is kind of very difficult to detect, right? And it's kind of very easy to make for new programmers, right? But let's save the function first and then give it a try and see. And then let's write a new script. Let's write a new script. And in this script, we're gonna call my Fibonacci basically. We're gonna call my Fibonacci. So n equals to let's give it like 15, and then f15. Let's just call f equals to my Fibonacci n, right? And then we can just disk num2 str n, and then what's supposed to come in front of it is f, right? F, and then f15, right? That's without any space. F15, and then it's supposed to have an equal sign, and then num2 str f, right? That's gonna be our display of the number. Let's just run it. Let's call it Fibonacci compare COMP, and f15 actually equals to 610, and it's actually a number that's identical to this number that we actually computed here, right? So it means that we actually got the right number. Right? So now let's sort of try to switch these two lines. Let's switch line 16 and line 17, right? Suppose we put this line after Control X after the assignment to B, and see if we still can get the right result, right? You see, it's completely wrong. And why? Why is that? Right? Why is that? Right? It looks like it's a kind of harmless change, right? But you actually have a logical error here, right? So when you actually assign C into B, the current value inside of the B is being destroyed, right? So as soon as you actually have done this assignment, the value inside of the C goes into B now, and the previous value inside of the B is destroyed. You have lost track of it, right? You didn't actually keep a record of it, right? And then at the second line here, you're assigning the value of B into A now. So what's actually the effect, right? As soon as you assign C to B, now after this assignment, B and C actually has the same value now. B and C have the same value, right? Because you have done the assignment. And then after you have assigned B to A, now A has a value of C now, right? So by the end of this particular statement, A, B, C all have the same value. And that's not exactly what you wanted, right? What you wanted is this kind of thing, right? So A must have the value of the previous B, and B must have the previous value of C, right? And if you do this thing, A, B, C, all of them are going to have exactly the same value as the C, right? And the correct space, let's change it back. Let's change it back. Right. If you look at the correct order, right? If you look at the correct order, right? As soon as C has been computed, right? The value inside of the A container becomes useless now. You don't really need the value inside of the A container in order to compute the next C. You don't really need it. So the value inside of the A container is completely useless now as soon as you actually finish computing the C, right? If you don't believe me, let's just go back to look at it, right? As soon as you got the C from A and B, for the next equation, what's actually useful is the value in B and C, right? Because you are going to need the value in B and C in order to compute the next C, right? The value inside of B and C goes into the A and B of the next iteration, right? So the value inside of A is useless, right? You don't need the value inside of A anymore. You can sort of see it, right? In the next iteration, all three arrows point. The first two arrows points to B and C. Only the B and the C in the current iteration is kind of useful for computing the C value in the next iteration, right? So the value stored in A is useless now, right? So what you can do is to actually assign B value into this useless into this A container. Right? It's okay to destroy the current value inside of the A container because their value is not going to be used for computing the C in the next iteration, right? So if you look at this assignment here, as soon as C is computed, as soon as we got the C, right, the value inside of the A container is not useful anymore because it's not useful, so you can override it, and we can override it by assigning B back to A, right? So the value inside of A has been destroyed, but it's okay, right? You don't really need it anymore for the next iteration, right? And then once you have assigned the value of B into A now, the B container is free to host the next value, right? Because the value inside of B already goes into A already. It's already being sort of already being reserved, right? Preserved. It has already been sort of we have already kept a record of the value inside of B now. So now B is free to take up on new values, right? And at this stage, we assign C to B, right? So the current value in B is going to be overwritten, but it's okay because that value has already gone into A already. We have kept a record of it, right? So now we can just assign C to B. It's going to override the old value in B, but it's okay, right? So now B and C actually goes into A and B, right? And that's something that we need to pay special attention to, right? Once we have made this correction, if we go back to the script, it's gonna give us the correct output, right? So now let's try to do a comparison, right? Now let's try to do a comparison. We're gonna start with a new Matlab section. Every time you want to start a new section, you just type 2 percentage signs next to each other. Then you start a new section. And this time we're going to implement the comparison with that explicit formula, right? We're going to implement the comparison with this particular explicit formula, right? And we're going to compare results obtained by using our iterative my Fibonacci function with this particular explicit formula. So let's try to, because I need to look at this equation in order to actually type it correctly. So let's put Matlab next to this equation. Right. Okay, so it looks like it's acceptable. So in order to do this comparison, we're gonna create two arrays. Basically, we're gonna create two arrays. Right? We're gonna call it Fib1 and Fib2. Right? Fib1 is gonna equal to zeros, one row. So let's do a big N. Big N is gonna equal to like 100. N columns, and then Fib2 is going to equal to zeros, one row, N columns. So we are going to compute this many Fibonacci numbers, 100 Fibonacci numbers, right? And then we're going to store those Fibonacci numbers into two arrays. One is called Fib1, and Fib1 is going to be used to store the Fibonacci numbers created by using our my Fibonacci function, and then Fib2 is going to be used to store the Fibonacci numbers computed using this particular explicit formula, right? And both Fibonacci numbers, both Fibonacci sequences are initialized by using this particular Matlab function, right? This Matlab function, which is called zeros, is going to create a Matlab matrix filled up with zeros, and then the input here that we are giving to this particular particular function called zeros is actually a Matlab vector or Matlab matrix. You can think of it as a Matlab vector because it's got like just two numbers in the same row. So let's think of it as a kind of a vector, right? It's got like two numbers, and then these two numbers are gonna be used to specify the dimension of this created zero matrix, right? So for its first dimension, it's gonna be 1. First dimension is gonna specify the row number, right? And then the second dimension is gonna specify the column number. So here we are basically asking Matlab to create a vector or a matrix with 1 row and n columns and filled up with zeros, basically, right? So if it's got just 1 row, we can think of it like a vector, right? But if it has more than 1 row, then it's a matrix, right? But now we are just creating a vector, right? So the first dimension is going to be 1. So it means that it's just 1 row and 100 columns. And Fib 2 is exactly the same thing. And then we're going to write another for loop. So for, let's call it n. N goes from 1, n goes from 0 to n subtract 1. Right. So if n starts with 0 and then ends with n subtract 1, that's exactly n numbers, capital N numbers, right? If you don't believe me, so suppose n equals to 10, right? And then 0 goes to 10 subtract 1, that's 9. That's exactly 10 numbers. And Matlab is actually telling you column 1 through 9, that's 0 to 9. And then column 10 is 9, right? So the total number of iterations is going to be exactly capital N, this many, right? So once we have the n, we can actually compute the Fibonacci number, right? We can compute the Fibonacci number. So if I want to use my Fibonacci, and then all I have to do is to give it an n as the input, right? And then the output is going to be assigned to where, right? It's going to be assigned to where. We're supposed to give it to Fib1, right? And then which element we want to use to actually store the nth Fibonacci number computed using our function, right? Which index? If I just put n here, it's not going to be correct, right? Because the n starts with 0. And in Matlab, if you try to index into a vector or matrix with the index of 0, then it's going to tell you you got a syntax error. So the smallest index in Matlab is always 1. You cannot actually index into a vector with the index 0. You cannot do that, right? But how do we actually shift the index from 0 to n subtract 1 to 1 to n, to 1 to capital N, right? It's actually quite easy. All we have to do is to add 1 to it, right? So when n, small n, has a value of 0, 0 plus 1 is 1, right? So we're assigning my Fibonacci 0 when n equals to 0 to Fib1 with the index of 1. And you have to sort of pay attention to the syntax. That's the that's the parenthesis here, right? In Matlab, if you want to index into a particular matrix, you use parentheses, right? And when you call functions, you use parentheses to group together the inputs, right? But when you try to concatenate together to construct a matrix or something, you use square brackets, right? Here we are basically just constructing a vector or matrix by concatenating two numbers, 1 and n here, right? So that's square bracket, right? But if you are trying to actually retrieve the number that's stored at a particular position inside of a matrix or array, you use parentheses, right? That's very, very important to actually remember. And then what's going to be Fib2, right? Fib2n plus 1. Fib2n plus 1 is going to equal to this particular very long formula, right? But it's okay. Let's try to write it. It's 1 plus sqrt 5, right, square root of 5, and then divided by 2, and then the whole thing has to be raised to the power of n, right? So that's this part of the equation, right? And then you have to subtract this part of the equation. Subtract. So 1 subtract square root of 5, and then divided by 2, right? Then divided by 2, and then the whole thing has to be raised to the nth power, right? So basically you've got this thing, subtract this thing now, and then this subtraction has to be enclosed inside of a pair of parentheses, right? And then the whole thing has to the whole thing has to divide by square root of 5. Divide sqrt 5 with a semicolon, right? It looks like a very long formula, but it's okay. It's okay. You can just type it one component at a time, right? And then we can construct figure 2, right? And that's sort of the second section of our code. And in the last section, let's try to create a figure and then make a plot of fib 1 and fib 2, right? So let's create a new figure. Let's just create a figure 1 with an input of 1, right? So figure is a function, and then this figure function is going to take a input, an optional input, right? That's the figure number. That's the figure number, right? If this figure already exists, if figure 1 already exists, then it's going to make the figure 1 active, becomes the active window, and then all the plots that we're going to make is going to be plotted into that figure 1, right? So what are we going to plot? What are we going to plot? We're going to plot fib 1 and fib 2. We're going to plot fib 1. And then what's going to be the horizontal axis for our fib 1, right? What's going to be the horizontal axis? By the end of the iteration, this value of n is going to take on a value of capital N subtract 1, right? It's not going to be a vector. It's not going to be a vector. But a plot is going to take two vectors of the same length, basically, right? So what we're going to do is that we're going to reassign n to 0 colon capital N subtract 1, right? So this line is actually inherently different from this line. It's actually very different from this line, right? This line is actually telling you that the for loop with the index of n is going to start loop from 0 and end with the value of n subtract 1. But here you're actually constructing a range, constructing a vector, horizontal row vector, and then assign that row vector into n. So in this particular statement, n is always going to be a scalar. It's just going to be a single number. But here, n is going to be a vector, right? And all the elements inside of n is going to go from 0 to n subtract 1, right? So we can use this n as our horizontal axis, right? So plot, this product function is going to take two inputs, the horizontal axis, n, right, which is a row vector, and then fib 1 is also a row vector, right? Fib 1 is already sort of constructed here, initialized here, and then all the values inside of the fib 1 is kind of automatically changed inside of this loop, right? And then let's specify the style of the line. Let's make it black, and then let's just make it as a line, right? So K means black, and then a dash just means that I want a line, right? I want to connect all the numbers, all the dots inside of that vector, right? And then that's sort of a basic call to the plot function, right? And now this curve is going to be plotted into figure 1, right? But at the same time, we also want to plot fib 2. If we just repeat the same plot command, if we just repeat it, Let's copy and paste it. Control C, and then Control V, and change Fib2, but maybe change a different color to R, right? If we just do that, then this, by the default behavior of Matlab, is that the curve made by this plot is going to overwrite the curve made by this plot. So you are not going to be able to see two curves on the same figure. You're going to see just the one curve, which is made the last, which is the one that's made the created by the last plot command. Right? If you want to see two curves on the same plot, there's a very important command that's called hold on. Hold on, this particular statement is going to tell Matlab that I want to hold on to the current plots and all the curves that's inside of the current plots. And all the new plots are going to be made on top of that existing plot. So it's not going to overwrite the existing plot. Right? If you want to sort of make multiple plots. Right? And now let's just run it. So it looks like the Fibonacci sequence actually increases very, very quickly, right? It actually has increased from like a very small value to a very large value in a pretty short range. It goes from 0 to 100. It increased from close to 0 to like 2.5 times 10 to the 20th power, right? 10 to the 20th power. So if we would like to sort of see the details, maybe we should just change the range of the calculation. Instead of computing like 100 numbers, let's compute like just sort of 50 numbers or something, right? And then because the red curve is kind of right on top of the black curve, maybe let's make the red curve a dashed line, right? So how do you actually specify dash line? You put two minus signs together. That's gonna give you a minus sign. That's gonna give you a dash line, right? But if we make this kind of change, because the current figure is hold on, right? So all the new figures are gonna be plotted on top of the old figures, right? But that's not what we really wanted. So what we might want to do is actually at the beginning of the script, we do a clear all, and then instead of close all, let's just I can kind of forget what's actually the command for clearing a figure window, right? COF, I think. Oh, so that's kind of correct. So we're gonna go into figure 1. We're gonna make figure 1 active, and then COF clear the window. Right? That's kind of our initialization step. And then we're gonna go back to figure 1 and remake those plots. Right. So now you can sort of see two curves. The black curve is kind of on the bottom, and then you can see red curves. And the red curve is kind of on top of the black curve, but it's because it's dashed, so you can still see some black dots here. Right? You can still see some black dots. If I want to zoom in, I can click on this button, which is going to allow me to zoom in. So if I want to sort of zoom into a particular section and examine the details, then I can do that, right? And you can sort of see the red and the black is kind of right on top of each other, right? But maybe you can try to adjust more. So for the Fib 1, we're going to use K line plus a star, right? And then for Fib 2, we're going to use with a circle, right? And see what's going to happen. Right. So now we can sort of see not just the curves, but also the locations, right? The locations of the dots. Right. If we want to zoom in, we can sort of select a portion and look at if they are indeed consistent, right? Right. So the kind of difference is kind of very, very small. It's almost indistinguishable. So another thing that we might want to do is to actually plot the difference, right? So let's plot in Fib 1 subtract Fib 2, and then still with a different curve. Let's call it B. and then we're gonna use B line, and then with a triangle as a symbol, right? And then let's rerun, right? So B with a triangle as a symbol is now the difference between these two, right? The difference between these two. But still, the range is like huge, goes from close to 0 to like 8 times 8 billion. That's 8 billion, right? It's close to 8 billion or something. If you try to zoom in to look at the blue curves, it's very, very small, I think. Right? It should be very, very small. The blue curves should be very small. Right? And another way to actually make the same plot is that to use subplots. Subplots, right? We can plot EB1 and EB2 in one subplot, and then plot the difference into another subplot, right? And then we can actually adjust the scale to look at the difference in a better scale, right? So if we want to make a subplot, we can use the subplot command. So here we're gonna do a subplot. What's gonna be the kind of subplots we want to use, right? M and P. So M specifies the row number of the subplots. Suppose we want a row, a plot with one row, subplot with one row but two sub windows, and then we're gonna plot into the first sub window, right? And then subplot still one row, two, but into the second sub window, right? We can do so. It's one row, two windows on two different window columns. Let's just run it and see what's going to be the effect, right? Yeah. Right. So the horizontal, so the vertical scale goes from 0 to 8 billion for this particular subplot, right? And then for this particular subplot, the vertical scale goes from like 0 to 10 to the minus 5th power, right? So as n becomes larger, the difference also becomes larger. Right, you have a slight increase in with the, but you can sort of see even though the error actually increases as n increases, but it increases a lot slower than the actual value, of the Fibonacci sequence, Fibonacci number, right? So this is increased a lot faster. So it goes from 0 to like 50. The order of magnitude is close to like 10 to the 10th power, right? But this the increase from 0 to 50 for the error actually increased a lot slower, right? It increased just by from the 0 to like 1.4 times 10 to the minus 5th power. So it means what? It means this this particular analytic formula that we have typed up is actually really accurate. This analytic formula, this explicit formula, is actually a really good approximation to the actual Fibonacci sequence. Okay, so this is kind of a long example, and we have covered a lot of ground in this particular example. We talked about the for loops, right? We actually looked at the 2 examples of for loops, and the difficulty is probably here. These 3 lines, how do you actually understand it, right? It's very, very difficult. It's especially for new programmers, it's kind of very difficult to fully understand the importance of the ordering of these 3 lines, right? And then we looked at how to actually make plots, right? How do we actually we're going to look at those how to make plots in Matlab in a lot more detail in later videos, right? And you will discover that Matlab actually has a very strong capability for making plots. It's sometimes people do the calculations using C or Fortran, right? And then they output the results and then load the results into Matlab, and just for the purpose of visualization. So Matlab actually has a very strong visualization capability. It's very much worth looking into, right? But by now we have sort of completed kind of a overall coverage about the flow control, right? We looked at the branching structure, and now we looked at the loops, right? Of course, Matlab provides another kind of very useful loop construct, which is called the while loop, right? And then for the branching structure, Matlab also provides the sort of switch statement, right? How do we actually use those things? Is going to be the topic of future videos.